Right. Hello, everyone. Welcome to another ACE Spotlight event. My name is Alireza Darbehani, and I'm a machine learning engineer at WSP Canada. I'm thrilled to have Dr. Akram Bayat, our speaker today. She is a postdoctoral associate at the MIT Media Lab. Akram received her PhD in computer science from University of Massachusetts Boston in 2018. During her PhD research, she worked on developing machine learning algorithms for practical real-world problems. And she was conducting experimental studies for modeling of human physical and behavioral characteristics using data from sensors, wearable technologies, and mobile phone. She's going to talk about human versus machine visual systems. And without further ado, please take us away, Akram.
Okay, thank you very much, Ali, for introducing. I'm actually very happy to be here and present part of my work that I did during my PhD under the supervision of Professor Mark Pomplin. The goal of today's talk is to investigate to which extent computer vision-based systems resemble human mechanisms for scene perception and object recognition in three problems that I will actually get to them in my next slide. And second, how we can enhance their performance. I will introduce three problem here, and I will compare those problems in human visual system and deep neural networks. The first problem is scene categorization. Human usually gets a gist of a scene before segmenting and grouping the objects. We define the gist as the initial representation of a scene that can be obtained in a brief glance. However, in deep neural networks, scene categorization are done based on the objects in that scene. For example, in a room, if we have the desk, a lamp, or a chair, the deep network will categorize it with a high probability as an office. The second problem is scene perception. Usually humans use scene grammar for efficient object recognition. But we define scene grammar as a consistent semantic relation between scene and its objects. For example, we don't expect to see a toilet paper in a dishwasher. But in deep neural networks, we know that most of the current scene classification networks don't learn semantic relation between the objects of a scene. The third problem is multi-resolution recognition. A human visual system contains multiple channels, and with each channel sensitive to different narrow range of spatial frequency. So it means if you give a low resolution image to a human, we still understand to recognize and see the objects. But in deep neural networks, it has been shown that the performance of deep networks drops significantly with low resolution images. So based on that, I actually talking about the first problem that human gets a gist of a scene before the segmentation and grouping the objects. Actually, the content of the gist usually includes a conceptual understanding of a scene. For example, we say this is a birthday party. That describes the spatial structure and functional aspect of the scene space that we refer to global scene properties. And this perceptual and semantic information comprehended in a single glance of a second in a scene, so usually between 13 or 250 milliseconds. But actually, the scene understanding has a dynamic nature. What that means? It means, for example, we have a scene categorization. For example, here we have a street. So we know what this scene about. But also, it's important to know the goals of scene understanding. For example, sometimes we search for a specific objects or for some specific information. For example, we have two objects here, yellow object and green object. In some other case, maybe we want to navigate from point A to point B. So we have another goal of the scene understanding. Based on the scene understanding, we may need a different type of information, as well as a spatial structure and functional aspect of the scene, as well as the scene categorization. As I said, global properties express a scene using high-level spatial and functional aspect of a scene in order to understand the dynamic nature of a scene. Three groups of global properties have been defined. The structure that express a scene openness, depth, and expansion. Scene content that express a scene naturalness and clutter, and scene constancy that express the scene's temperature and transience. For example, we have two images here from the same scene in two different seasons. Both of them are natural. That comes back to the structure. Both are, back to scene content. Both actually are closed, so it means less navigable. The left side is highly transient, but the right is non-transient. The left is actually high temperature, so means summer or spring, and the right one is winter, so low temperature. So based on the global properties I defined here, I'm going to focus on one of the dominant global properties, so it means openness. So experimental study shows openness is an important descriptor of the shape of a scene and a key process for holistic perception. That's why in today's talk, I'm going to focus on this global property. In deep neural networks, as you can see in this image, we usually have a scene that we categorize the scene that we call it basic level categorization. For example, here we have an office. But the question is, can these deep learning networks and the representation that we learn in the inner layer of these deep networks represent the global properties of a scene similar to human visual systems that gives us some spatial structures and functional aspects of a scene before grouping and segmentation? In deep neural networks, it has been shown that the object detector, even for scene recognition, object detectors emerge in the last layer of the deep networks. But we want to get the global property or a gist of the scene before segmentation and grouping. So we want to have a parallel pathway here that gets the information from the representation we learn in the deep scene networks in order to do superordinate categorization, which means extract the global properties of a scene. For example, this scene is man-made. We're talking about the content of a scene, and it's closed. And we're talking about the structure of a scene. For this purpose, we actually got the data from our collaborators at Wright State University. They conducted a big experiment on Amazon Mechanical Turk machine. So they actually worked with 1,055 subjects. They used the 7K images from some database. And they actually gave a pair of the images to the subjects and asked them which scene is more, for example, natural, which scene is more close. Based on the results, they create some subject reference ranking scale for each image using the Bradley-Torrey model that estimates the probability of pairwise comparison. For example, here you can see in the left side, I have some pictures. In the top row, we have the picture that are more close, and the bottom row shows the picture that are more open. In the ranking in the right side, you can see even between the more close scenes, for example, one is more close than the three. Let's move on to the next. So here we are going to assign the ground truth categories for the 7,000 scene images we have. Each actually blue dots here shows an image in our database. And we have the ranking of each image based on their close and open scores. We use the linear regression to model relation between the open versus closed. We then split the this line into 3 equal parts. Image on the, as you can see, image that are located in this part of the, the coordinates are highly closed because the value of close is more than the open. And we have the images here that are highly open. So totally we have about 2K image highly open, 1,300 image as a highly closed. But we have some images between that we can't say they are highly closed or highly open. Suppose we have a room that the window is open. So the subjects can interpret this as can decide if this is a closed or open. So these kind of images have been actually scored as a medium open closed. During the training, we try to use strong ground truth, so means we use the highly open and highly closed images. But medium open and closed, we use an algorithm that I explain later, that how we can actually decide about these actual images. The algorithm is like this. We have open set closed ground truths. So we say for a given image, considering the both regression result and subjective ranking result, if the both results actually, if the open ranking is greater than the closed ranking, in both results, we label it as open. If the closed ranking is less than the open ranking, in both results, we label it closed. Otherwise, it's neither open nor closed, and we remove the corresponding image from the data. We put the images that resulted from this algorithm in the test medium set, and we use it for just tests during our deep learning, developing our deep learning model. In order to extract the global properties of a scene, we use the deep networks VGG16 that has been trained on Places 365 images. So VGG16 shows a state-of-the-art performance in scene recognition. That's why we use it. We actually feed our open set and closed set to these networks, and we extract the features from different layers of the convolutional networks, from convolutional layer 1, 3, and etc. We extract the features and we train the support vector machine using the features we have extracted from the different layers of the convolutional neural networks to classify them as open or closed. We also evaluate the role of low spatial frequency information of visual images for processing of global properties in deep convolutional networks. We define a spatial frequency as a measure of how often components of image structure repeat across units of distance. And we choose low spatial frequency because it contains more information about the scene gist as well as global attributes of the scene. So we one time we extract information in full spectrum, and the next time we extract information in low spatial frequencies. Here you can see the results of support vector machine for classification of the features based on the open image, based on the open and closed state of a scene. So the result of classification here, as you can see, shows that the effectiveness of the deep features that extracted in the first layer of the network to distinguish between openness and closedness state of a scene. Also, we can see that propose the features in deeper layer of the networks does not seem to be useful for representing a scene at the superordinate level or for presenting the global properties of a scene. However, we know that it's necessary for categorization of the image at basic level Furthermore, using deep layer features decreases the classification accuracy, as you can see here, especially for the images with the medium level of openness that you can see with the gray color. Also, the low spatial frequency and full spatial frequency represent the similar results. Um, and so we can conclude that the convolutional units of the first layer of VGG610 plus S65 network are well suited for predicting a global properties, openness of state of the image, and this is like a human visual perception because we can recognize the structure of a scene before we do segmentation and grouping, similar to the deep network that we could extract the global property in the first layer of the networks. And in the deeper layer, however, we actually do the object detectors emerge, and we can actually, based on that, do scene categorization. Also, the predicted global property can be used to enhance the performance and interpretation of the scene recognition task because it can represent a scene as a different level but describing its holistic structure. This level of representation is not an alternative for the current deep neural networks that categorize a scene at the basic level. However, it's a parallel pathway to add information to it. So here, actually, I would like to ask if anyone have a question about this topic, the global properties, and then I will move on to next topic.
Yeah, there is actually one question which just came in. Can you recap the openness and closeness concept? What do they mean actually in the images?
Exactly. So I would like to show it here. And when we talk about the openness or closeness, we talk about the spatial structure of a scene. So it shows how navigability is in your scene. For example, if in this scene or in the closed another best example for that is this one here. For example, when we talk about the open and close, we mostly talk about the functionality of that image. For example, in the image 1, you can see you can navigate that much, right? Comparing to the image number 4, because it's number 4 is more open and number 1 is more closed. So we talked about the spatial structures and kind of the structure of a scene that you can navigate. So it's mostly can be useful for robot navigation. For example, depending on your application on the for scene recognition, what's your purpose? So sometimes you need to know how much you have the ability to navigate in a scene. So because of that, we define open and closed.
Gotcha. Also, like how does it help? Is it like helpful when we want to classify images based on the general properties of an image?
Yeah, it's actually it doesn't help for the basic level categorization in the deep networks because, as I said, for basic level categorization, we only talking about the what is the scene about. For example, here I say this is a street or this is office, right? But when I talk about the global properties, I'm talking about the functionality. I'm talking about the spatial structure. So it means it depends more about the dynamic nature of the scene and your goal for scene understanding. For example, in this image, we say this is a street, but depending on my goal, for example, I may want to recognize the objects, right? Or maybe my goal is to navigate from point A to point B. So depending on your goal, we can add more information to the basic level categorization. So it's kind of complementary information as well as the basic level categorization, and actually gives you a more understanding of the nature of the scene based on its dynamic nature.
Right. Very good. Let me check if there is any. There is one more question. Is it related to depth perceptions? Someone asked if it's related to the depth perception.
Yes, actually, openness is not the depth, but it's related to depth and expansion because all of these three, openness, depth, and expansion, are part of a global property, structural global properties. So all of these three that I defined, seven global properties that I defined here, open, depth, expansion, naturalness, clutter, temperature, and transience, are global properties that each of them can add some information depending on the application that we do scene recognition.
Right, right. It's my own question. What applications does this type of like scene recognition, for example, help with?
Actually, this kind of scene recognition, I said this is a complementary information about the basic level categorization. For example, for robot navigation, you can use it because as well as having the basic level categorization that explain what is this scene about, you can actually get some information about the functionality of that, how much it's navigable or not. So it also has other kind of application that you can actually read in the literature. It's not in the scope of this talk, but actually I could say this actually adding more information about the scene you have.
Right, right. Gotcha. There is one more question. So interpretation is based on actor that acts within an environment. So is it very much like reinforcement learning?
Not really. Because reinforcement learning is based on the rewards you get, the feedback you get from environment, right? But this is already, it's about the information is in the scene, but it depends to your goal, right? Why you want to understand it. So I don't see any strong connection between this, but that's a great question. I can think about it.
Yeah.
Yeah.
Okay. Sounds good. Sounds
Yes.
good. So yeah, I guess these are all the questions we have. I guess you can continue with the next section of the presentation.
If you remember, the second, the problem I talked was about the scene grammar, and the third one was about the multi-resolution. But actually, I would like to explain the multi-resolution because actually it's very interesting concepts in the deep neural networks. In the human visual system, we usually have the multiple spatial frequency channels of human visual system. So it means each channel is sensitive to a different spatial frequency. However, in deep neural networks, we actually did the experiment and we see that usually the networks we have been trained and tested on full resolution and high resolution images. So our motivation for this work is that how deep neural networks perform for different spatial frequency bands, or what happens if we feed a low resolution image to our deep neural network. Before actually going to that concept, I would like to introduce two core object recognition concepts in human visual system. For object recognition, human eyes sample a large amount of information at the center of the gaze, as you can see here, and try to filter out the rest of the image in the periphery of the periphery area. So it means we actually have high frequency information, special frequency information here, but we have tried to sample just a little information from the rest of the scene. Another core object recognition concepts in human visual system is that the contextual information plays an important role. Here, I would like to ask a few questions here. I have a low resolution image. I cut several bounding box of the different image I have. So can you guess what this actually image is? I guess it's difficult.
Not really.
How about this one?
No, it's hard to guess.
Yeah, and how about this one? I guess it's much harder.
It's even harder. Yes.
Yes. So now this is the image. Can you tell me? So this is actually
Yeah,
the car, right? This is a
that's
dog, and this is a human. And you can see how contextual information are important when we have the low resolution image, right? So this is how the human multiple frequency, multiple channels help us to understand the images in different resolutions. So here, actually, I would like to tell you how the deep neural networks works when we feed a low resolution image. I'm working with the RCNN because actually Faster-RCNN because it's one of the state-of-the-art networks for object recognition. I have the image here. I try to apply to Gaussian filter to remove the noise or high frequency information. At the full spectrum, you can see the classification, the object recognition performance here. It's at the top. So I decrease the resolution by applying a Gaussian filter. So I systematically create a Gaussian filter. I apply it, and every time I decrease the resolution. As you can see here, when I decrease the resolution, the performance drops. Again, I blur image a little more. You can see the performance drops, and a little more. Again, performance drops. And here, that you can see the performance of the deep networks is about 0. But we still, as a human, are able to see and understand the scene, right? So for this, we create 20 sets of image database whose resolution varies systematically from extremely coarse to very fine in 20 scale resolution. And this is performed by applying the two-dimensional Gaussian low-pass filter in various cutoff frequency. So we create 20 data sets in different resolution. We use the Pascal VOC dataset for this, for the image. And we have train the faster RCNN in different with different data sets. For example, here I create 5 models that each have been trained on different resolution input images. So I only from the 20 image data sets, I train only the RCNN on 5 frequency range, and I create 5 models. One that has been trained on the full model, full spectrum, that we call it full model. One has been trained on 20 over 20. 20 over 20 is similar to the full spectrum. It's like removing the noise, high frequency noise. 18 over 20, 10 over 20, and 5 over 20. The reason is that these networks, actually the results shows work similar to other range of frequency that are actually close to their bandwidth. This is very interesting results. If you can see this image, full model is not able to detect the second person. 20 over 20 model even is not able to detect the second person, but 18 over 20 model and 10 over 20 model are able to detect this person with high resolution. So it means this model can generalize to a wider range of frequency than the full spectrum model. Here you can see the results of Faster-RCNN that have been trained on different resolutions. Here you can see the database resolutions that we have used, and here you can see the model performance. You can see that the models that are trained on a slightly lower resolution, it means 20 over 20, outperform the full spectrum model, even for the input image that are full spectrum. Models that are trained on low resolution image, for example, R10 and R5 that we have here, exhibit significant robust improvement in recognition of low resolution image. At the beginning, they had very low resolution, 45%, but with training the 5 over 20 model, we increased it to 61.3%. After training this 5 model, I try to combine them together because I would like to, when you feed an image, regardless of the resolution of the image, we want to be able to, with high performance, we want to recognize the objects. So what we do is that in each of these models, we extract the bounding box of each, the best candidates of the objects, and then we use non-maximum superagent to remove high overlap bounding box, and then we choose the objects in this multi-resolution Faster-RCNN model. As you can see, the result of object detection from 5 models can be obtained, and here I will show you the results of integrating these 5 models. This is the coordinates. The x coordinate shows the resolution of the input image, and the y coordinate shows the mean average precision. This is for full model. If I go to 20/20 model, you can see it works a little bit in different resolution. It works a little better than full model. If I move to 18/20 model, it's similar to the 20/20. I go to 10/20. As you can see, it works better in the low resolution images. I move to the 5/20. It even works better in the lower resolutions, as you can see here with the blue. Now I integrate these models based on the previous slide that I explained, that I show you with green. And you can see that you have the good performance comparing the full resolution model that we have with the light blue here. You can see the green one have the great performance in the all resolutions. So before moving to the next concept, which is the scene grammar, I would like to know if anyone have a question. I will be happy to answer. Ali, can you hear me?
Yeah, sorry, I was muted. So I haven't received any question, but can you explain like the difference between the models? I think I missed something between like the 20/20 versus like 18/20 versus the full resolution.
Yes. So actually, I said we have the full resolution images, right? So we can apply the filter to create the different resolution database, right? So this is system. I applied systematically. I define. I actually here, as you can see, I create a different cutoff frequency. So it means I apply 20 Gaussian filter to my database, which is Pascal VOC.
Right.
So I train RCNN each on different resolution input images. So one time I train it on the full resolution images. Next time I train it on the 20/20 model. The next time I train it on the 18/20, 10/20, and 5/20. So I will have 5 models that have been trained in 5 different resolutions.
Right. Now it makes sense. And some of the lower resolutions models actually like beat the full resolution,
Exactly.
like generalized better too.
Exactly, yes.
Okay.
Here, as you can see, especially 20/20 is similar to the full spectrum, but we remove some noise. So you can see outperform the full spectrum, even for different input resolutions. And when we move to the lower resolution, the models that have been trained on the low resolution image, you can see the performance in the dark blue. You can see it's much better than the full resolution. And when we integrate and combine these models together, that you can see with the green, we outperform all of these models. So it means if you apply an image to this actually a combined model, regardless of the resolution, that is low resolution or high resolution, we still have the very good performance.
Right. Very interesting.
Yeah. Okay. How much time we have? Can I move to the next?
Yeah. Yeah, we still have time.
So the next concept is the scene grammar. I said that we define the scene grammar in human as a semantic relationship between the objects. So it means, for example, we don't expect to see a toilet paper inside the dishwasher, right? So we create some, so there is a consistent relation between the objects that we have in a scene. But in human, we don't have, in deep neural networks, we don't have such a semantic relationship between the objects. My goal in this project was to define to which extent the deep neural networks can understand the scene grammar. So for this, for example, first of all, I would like to show it in an image. For example, here we have a glass on the table, right? Here we have a sponge, but this is obviously violate the synthetic and semantic rules because it hangs in the air, first of all. So it violates this, the synthetic relationship and rules. And also, we don't expect to see these objects in the bedroom. So it violates the semantic, actually, rules. So in each for human, in this image, everything is considered as a consistent object, but in the right side we say we have inconsistent objects. But we would like to know the influence of inconsistently on the deep object and recognition networks. So again, we compare the human versus the deep neural networks to understand how scene grammar have been applied in the deep neural networks. For this, we use a SceneGram database. It consists of 62 real-world indoor scenes in 2 consistently conditions that contain semantic and synthetic violations. We use this data set. I apply this data set as an input to my classification networks for scene recognition and object recognition. As you can see, when we have a consistent scene, we have you can see the top 1 error and for the scene recognition and object recognition networks. When I manipulate, actually, when we manipulate the images like this, so we remove the consistent objects and replace it with the inconsistent objects, you can see the performance of the networks drops or the error increase in the network. So here you can see one of the results that we got. So we actually visualize the discriminative regions in different consistency condition. So here we have a kitchen. So you can see that it has been classified as a kitchen, and the discriminative region using the class activation map shows that these objects actually lead to this classification results. We add inconsistent objects here, watercolor, to the scene, and again we visualize the classification results based on the discriminative regions we have. You can see that the results of classification change to the shower, and you can see how however this object is not consistent in the scene. For the human, actually we still know this is a kitchen, but it shows the classification results in the deep neural networks. So this is very interesting. So we go to the next step to see how we can actually find the ground truth. We know that human can understand the scene grammar, so we can consider the human eye movement as a ground truth for scene grammar understanding. Because of that, we did an experiment to collect the human eye movement. We hired 20 subjects to participate in our experiment. We showed them 124 images to each subject. Each image was on the screen for 5 seconds. Participants were asked to decide about the scene consistently condition and say it's consistent or it's not. One of the, actually, some of these images are actually regular images. Some of them has manipulated objects that violate the scene grammar. So here you can see very interesting results for the 20 subjects. As you can see, the number of fixations on the consistent objects, as you can see, is less than inconsistent objects. It shows the direction of attention of the human on inconsistent objects. Also, the number of fixation before the target, you can see in consistent image is more than inconsistent, because once the subjects find the inconsistent objects, stop searching the scene, because focus on that inconsistent objects. Also, the average fixation duration you can see on inconsistent object is much more, because this is inconsistent with the scene content. So it shows that we can use the human fixation map as a ground truth to see, to find the relationship between the objects. We create a binary fixation, and then based on that, we create a continuous fixation map. The reason is that we would like to compare the saliency maps we get from the deeper layer of the networks when we feed the inconsistent images to our networks, and compare it with the ground truth human eye movement. Here, for example, you can see two images. One of them has inconsistent objects, and other one is regular. Here, you can see a distributed eye movement here, but in the inconsistent object, we have actually high density of eye movement here. What we do here, actually, we extract the saliency map from the deeper layer of the networks that we feed actually to these two images, and we try to compare this saliency map with the human eye movement. And you can see, for example, in this image, you can see the ROC curve with AUC scores for two different images, and you can see this is much better than this one where we have inconsistent image. So actually, I don't want to go. We did lots of experiment with this with the inconsistent scene, but we couldn't train any networks for inconsistent objects because we didn't have enough data set, and it was not at that time was possible to create those manipulated images with inconsistent objects. But what we did in this project, to create kind of a platform for the next research to be able to actually define a scene grammar in deep neural networks. Based on my research, and in that time, we can conclude that class-specific saliency map that we actually got from the last layer of the deep network poorly perform in predicting the human fixation location in inconsistent scene compared to consistent scene. And future direction of this work is to create a larger data set with inconsistent objects or actions to train a saliency map that can predict inconsistently in a scene. So, is there any question?
Sounds good. Let me check the chat and see if there is any other question. I have one question myself. So how do we know if the eye movements and the attention of the human eye movements in an inconsistent scene isn't because of the object itself rather than detecting the inconsistency?
That's a great question. So actually, this is actually the question that you can answer through the experiment. So it's very important your experiment to be in control condition. For example, sometimes if my manipulated objects, for example here, if very big, it's very likely that my attention is because of the size of the image, right? Or maybe if I have manipulated images in the center of the scene, it may affect my attention because it's in the center of the scene, and we know that human, first of all, look at the center of a scene. So it's very important that we consider those conditions when we design our experiments. But what I did in part of my actually work that to try to actually extract some only images that have less variability. So
Right.
yes, so it means we try not to put very salient objects in a scene when we want to analyze the human eye movement. So it means we give it the same actually probability or likelihood for the human to search different type of the images.
Right, right. Very interesting. Somebody asked that what is the plan for creating the larger data set for this particular film? Yeah.
Yeah, that's a great question. I was very interested to continue this research area because we have lots of research in scene grammar for the analysis of human visual system and how the human actually understand the scene, but we don't have it in the deep neural networks. So my plan was to create some inconsistent objects, but it needs time because you have to, as I said, create some control condition, right? So make sure the images you use, the objects you manipulate are actually can give a good understanding of relation between the objects and try to train it. So if anyone is interested, I'm very happy to collaborate and actually design experiment to actually create those database.
Awesome. So if someone is interested, you can find Akram's contacts on the events page, and also at the end of this presentation, probably. Yeah, feel free to reach out. Someone asked, can you use simulated scenes to create the data set? Like maybe like a scene created by the game engine or something like that?
We can, but actually it's very important that when we want to compare two scenes, the illumination, everything should be same in the scene. So we should make sure that everything, as I said, between two scenes are the same. But yes, we can use them. Yeah. But again, what kind of objects we want to use and other things we should plan for it.
Cool. Okay, yeah, and someone just mentioned, and I think you tried that apparently, especially here in this image on the page, like, or rather than using simulated area, use the scene and add some inconsistency to it, like inconsistent object in
Right.
Photoshop or whatever.
Exactly. Yes. Yeah.
Okay. Okay. Cool. Somebody asked, how is human perception used to increase accuracy in computer vision? It's a very generic question.
Yeah. So as I said, for human, actually object recognition scene perception is very efficient, and because of the several techniques that human actually use for these tasks. For example, as I said, there are several rules. One of the rules is the scene grammar. Uh, we learn the semantic relation between the objects. So that's why we first of all try to understand the scene at the beginning, create relationship between the objects. Another thing is that we efficiently, at a very short period of time, I mentioned between 13 milliseconds to 250 milliseconds, we understand the gist of a scene, what this scene about, and then go to next step, which is object recognition, grouping, segmenting, and understanding the relation between the objects. But in deep neural networks, it's vice versa. So it means we have the deep networks, we want to do the scene classification, but actually we do object recognition first, and then based on the objects we have, we decide about the scene categorization. So it's completely it's against what we do in the actually human does in understanding a scene. I believe if we want to improve it, we have to actually create this actual path. How we can first of all get the gist of a scene. Based on that gist of a scene, we try to understand the scene. And also, I should add this in the scene recognition networks. If the objects that you find during this process is much accurate, so you will have better scene recognition. So it's completely depends to the objects you have in the scene, but it's not what we have in the human visual system.
Right.
I don't know if I answered the question or not, but yes.
The person who asked the question said, I meant human perception in labeling data sets and in turn increase accuracy.
Oh, sorry, I think I under. Okay, so yeah, so the labeling of the scenes, for sure, it's actually affects, right? But the question is, when we actually create some standard database, they don't rely on the only one person's labeling. They try to do it, actually it's the crowdsourcing, so they try to get the actually votes of the scene from several subjects at least, and try to get the majority, do the majority voting, get the scene. So our for the standard data set, we have the standard actual labels.
Okay. Like the last call for questions. If someone has any question, please post in the chat. If not, so out of curiosity, I have a question myself. So how does, like, have you your team or you thought about like how this could be combined with the other models like used for object detection to achieve a specific task or improve the performance on a specific task?
Are you talking about the scene grammar or in total each of the
Well,
concepts?
in general, any of these concepts you mentioned in the presentation.
Yeah, in the first one that I talked about, the global property, yes, exactly. I created the model with the features I have, so it can be generalized to any model. So it means you can actually extract the features from the initial layers, and we use it for we use some classification methods like SVM, as I showed, to add the global property to the scene classification. So it can be added to any model. About the multi-resolution, I created the model, so it means we have the current networks, we can train them on we can choose different frequencies, special frequency, and they train the networks on those and combine them. And I showed that the combination of the models doesn't affect the speed of the networks for recognition. So it can improve and can be generalized to any other type of the deep architectures and deep network, deep learning models. For the scene grammar, we just created some study for understanding of scene grammar, but we didn't develop any deep learning networks. But in future, I would like to pay attention and see what we can do about this.
Sounds good. Very interesting. Somebody also asked, like, I think this is more of a general computer vision question. So what do we do when we have a limited data set? For example, let's say we have like the sign language detection task, and we want to increase the accuracy with the video or limited video or images of gestures.
Usually in this kind of task, we need to use the transfer learning, because transfer learning shows that it can be used when we have the limited data, because lots of the features we learn are low-level features that are actually common even between two different modalities. For example, in the natural image, we can use the current networks we have, for example, in different areas, but it has been shown right now at MIT, my research focus on pathology image analysis, but that's interesting that I have trained a model that have been trained on the image data sets. and it improved the performance of actually classification of cancer significantly. So it means when you have the actually few data sets, you have to use the transfer learning, and it's better to use the previously models that have been created in that specific domain, or if you don't have it, use the natural images. The second thing is about the architecture. Some architectures of deep learning can work with the limited data. So you can go and check them because depending on application, you can find different architectures that have been shown even with the limited data can give you best results.
Awesome. Sounds good. Yeah, the transfer learning is always practical because it also requires less resources to use for the training.
Sorry, can I add, because I just remembered.
Sure.
And also another thing is the synthesized images. You can, if it's sometimes you can use the augmentation to have more actually image, to add more image to your actually data sets, or synthesized image. You can use the generative models to create those synthesized image.
Yeah, sounds good. Sounds good. If you have any last word, or want to recap the conversation,
Sure.
please feel free to do, and then we can close.
Well, thank you so much. I'm very happy. Actually, I was able to present my work today, and I'm always open to any questions. Please feel free to send me email if you need some mentoring or anything. I will be happy to help.
Awesome. So then, as the last few words, I would like to thank you so much for your time, and we are glad to have you in our team. And thank you so much, the audience, for paying attention to the presentation. If you are interested more in similar talks, you can go to our website, ai.science, and sign up there to get notifications for the new future talks. And if there is nothing else, I would like to close the call. Thanks.
Thank you.